This is the video for our section on nonlinear systems. Before you watch this video, you should read the reading assignment that was on the guided practice. So if you haven't done so, turn off this video, go read your reading. Okay, so now that you have read that assignment, let's remind ourselves what sort of problem we're considering. We're going to consider a 2x2 system of differential equations, but these systems can be nonlinear. We are going to assume that they are autonomous, however. So dx dt is some function of f that we'll call f that depends on x and y, and dy dt is some function g that depends on x and y. And for notation, we'll just refer to that system as system star. So from your reading, you know that the way we are going to analyze these nonlinear systems is that first we are going to find their equilibrium points, x bar, y bar. And what are the equilibrium points? They're the points such that both f of x bar, y bar equals 0 and g of x bar, y bar equals 0. And once we find the critical points or the equilibrium points, we can use the Jacobian matrix at our critical points to linearize our system at that point. Now, in the reading, you saw why this is true, so why we can use the Jacobian matrix. And the key to this analysis is really kind of cool. So the key is that near our critical points, this nonlinear system looks like the linear system, u prime v prime equals the Jacobian matrix at x bar y bar times uv. So the whole idea is that we're going to find equilibrium points, we're going to linearize the system at each of those equilibrium points, and then we're going to classify those equilibrium points in the same way that we classified equilibrium points in the linear case. And then we'll combine all of them together and be able to sketch one large phase portrait. So that's the plan of attack. We're turning a global problem into a local problem. So problem near each equilibrium point. So let's look at an example. Let's take the nonlinear system x prime equals negative x plus xy, and y prime equals 4y minus 2xy. And if you've seen some math modeling, you might recognize this as a predator-prey system, but if you haven't, don't worry about it. So our goal here is we'd like to classify the equilibrium points, and we'd like to sketch a phase portrait for this system. So the first thing we need to do is we need to actually find the equilibrium points. So we need to solve the system of equations, negative x plus xy equals 0, and 4y minus 2xy equals 0. And remember, a critical point has to satisfy both of those equations. So you have to solve this system simultaneously. So if we factor both the first and second equation, we get x times the quantity negative 1 plus y equals 0, and y times the quantity 4 minus 2x equals 0. So let's look at what numbers solve the first equation and see what that tells us about the second equation. So notice in the first equation, one way to solve the first equation is for x to equal 0. Then if x equals 0, if I put that in to the second equation, that means we have the equation y times 4 minus 2 times 0 equals 0, which of course means y equals 0. Now the second way that the first equation could equal 0 is if y equals 1. So if I plug y equal 1 into the second equation, I get 1 times 4 minus 2x equals 0, which means x equals 2. So my conclusion is that my equilibrium points, or my critical points, are 0, 0 and 2, 1. So now, what am I going to do? I'm going to linearize my system at both of those 2 points and see what the local picture looks like. So remember our functions f and g in the notation that we started the video with. F is negative x plus xy, g is 4y minus 2xy. My Jacobian matrix is df dx, df dy, dg dx, dg dy. So if I take my partial derivatives of f and g, I get the matrix -1 plus y, x, -2y, 4 minus 2x. Now I want to look at the Jacobian matrix at each of my critical points, and that is going to tell me what the linear system at that point looks like. So at 0, 0, if I plug in 0 for x and 0 for y into my Jacobian matrix, I get the matrix -1, 0, 0, 4. And I can analyze that very quickly, you might see, but you should pause the video and check this for yourself. My eigenvalues are lambda equals 4 and -1, and then my eigenvectors are the vectors 0, 1, and 1, 0. So, near 0, 0, my solution should look like C1 times 0, 1 e to the 4t plus C2 times 1, 0 e to the -t. So my phase portrait near 0, 0 looks like this. Along the y-axis, I am moving away from the fixed point because that's the direction corresponding to e to the 4t. Along the x-axis, I'm moving towards the origin because that's the direction corresponding to -t, e to the -t, and then I fill in my curves accordingly. Now we'll do the same thing, but we'll do it at my other equilibrium point, at the point 2, 1. So in this case, my Jacobian matrix becomes 0, 2, -2, 0, and you should find the eigenvalues and eigenvectors for this matrix. And if you do that, you'll find that your eigenvalues are plus and minus 2i, so we need to do a little bit of analysis to see what the general solution looks like near this equilibrium point. So you can find your eigenvector is -i, 1. So remember, we split that into its real and imaginary components. So b1 is 0, 1, b2 is -1, 0. And by our theorem from the linear systems section, we see that our solution near to 1 looks like C1 b1 cosine 2t minus b2 sine 2t plus C2 b2 cosine 2t plus b1 sine 2t. And in particular, what does our phase portrait look near there? Well, it looks like little closed curves around the fixed point. So we call this a center. That's the kind of critical point that 2, 1 is. Now, my last step in drawing the phase portrait for the whole nonlinear system is to combine these two local pictures. And if I do this, I should get a phase portrait that looks roughly as shown. And so what you can see is if you have a starting point in various regions of the plane, this would give you some idea about what your solution, what your trajectories might look like in the phase plane.